Okay, hi everyone. In this screencast, what I'm going to do is begin and talk about the very beginning parts of the calculus involved in polar curves. Sorry about that. I was just distracted by something else that popped on my other computer screen sitting right in front of my face. So the first thing I'm going to have you do here is go ahead and sketch this cardioid, which I did over here. So go ahead and sketch it. Maybe you'll grab some polar graph paper too for this screencast because that's going to be helpful for you. All right. And as you get this cardioid all set, I'm going to just make sure that we go into this next piece here, really understanding two important differences. When we have an equation such as this, and we're talking about tangent lines. I think Jabril asked today about like slopes of tangent lines in this polar world and derivatives in general. Well, let's talk about that right now, and let's make sure we take this from a point where we really are understanding what an instantaneous rate of change means. If I look at this equation right here, where r is a function of theta, if I take the derivative, okay, of this equation, I'm taking the derivative with respect to the independent variable. So I'm taking the derivative with respect to theta of r and the derivative with respect to theta of 3 minus 3 sine theta, okay? And I think it's not too much of a stretch for us to get now then to this place. So dr d theta equals negative 3 cos theta. But now I'm going to ask you this question. How about dr d theta at theta equals 0? And when we calculate this derivative, dr d theta at theta equals 0, we're going to get the value negative 3. And let's talk about what this means. So this negative 3 here is it's absolutely not the slope of the line tangent to this cardioid at this point when theta equals 0. All right? We have to understand what the derivative means. And it almost feels like we're going way back to the days when we talked about what instantaneous rate of change means. Well, if dr d theta is our instantaneous rate of change, then this is really the instantaneous rate of change of r. Okay, and the instantaneous rate of change of r really is the same thing as the instantaneous rate of change of r, or the distance to the origin, okay, as a function of theta. So if you think about this here, and if this is our curve, and if I look at this, and I'm seeing that, when I trace this curve, when theta equals 0, right, because when theta equals 0, I get r equals 3. At this moment, right, at this moment when theta equals 0, what is the curve doing? Well, the curve is going in this direction. It's heading in this direction towards the origin. At that moment in time, the distance, or this curve, is curving towards the origin, and towards the origin because this is negative, so r is decreasing, and r is, again, the distance between a point on this curve and the origin. The distance between a point on the curve and the origin is decreasing at the rate of 3 units per, radian, right? So because the independent variable is in terms of theta is in terms of radians. So that's what this means. Another way of thinking about it here is, because this number is less than 0, the curve is heading towards the origin as opposed to away. because at that moment in time, right, if the curve was actually moving away from the origin, dr d theta would be bigger. So that's really important. That's an important point to make, that dr d theta is not dy dx. Now, what is dy dx? Well, remember what I said on the very first day. If you think about this polar axes, there's always, and some polar axes will actually have the xy kind of right on top of it, and you'll even see the xy labeled on top of it. Even in the polar world, the slope of the line tangent, that's dy dx. Dy dx is the slope of the tangent line. And if I go over here to this point again, so here's the point when theta equals 0, here is the tangent line. Okay, there is the tangent line. And I want to know what dy dx is. What is dy dx at that moment when theta equals 0, right? What does that equal? Well, this is where last year you derived this in BC Part 1. And those of you who were in AB last year, you derived this 2 years ago in BC Part 1. And those of you who weren't in BC Part 1, like Kate, you've never seen this before. So what I'm going to do is I'm going to tell you what dy dx is in the polar world. Okay, dy dx in the polar world, dy dx equals r times cosine of theta plus sine theta times dr d theta, all divided by negative r sine theta plus cos theta times dr d theta. What I did in a separate screencast, and it's on your calendar, I think it's even on this same day in your calendar, I just did this derivation. It's a 2-minute screencast if you want to see where it comes from. It's not very difficult at all. I just didn't want to congest this screencast. I think I may have even called it derivation optional screencast if you want to see where this came from. But you are going to want to memorize this. This is how you figure out what dy dx is from a polar curve. So let's go over here. Well, what is dy dx at theta equals 0 for this curve where r equals 3 minus 3 sine theta? Well, let's just find all the things we need here. If r equals 3 minus 3 sine theta, dr d theta is going to equal negative 3 cos theta. That means, let's see, dy dx at the point when theta equals 0 is going to equal, let's see, do you see this r times cos theta right here? See this r, whoops, what's going on? R is going to be r right here. So it's going to be 3 minus 3 sine of 0, all of that times, right? Now see this cos theta times the cosine of 0 plus the sine of 0, all of that times negative 3 cosine of 0. Whoops. And again, I know that some of you are seeing that I could have zeroed out some things and just showing all the work the first time through. Okay. This is now all divided by, again, negative r sine theta. So negative 3 minus 3 sine 0 times the sine, whoops, this should be a 0, excuse me, times the sine of 0 plus cosine of 0 times dr d theta negative 3 cos 0. Whoops, what's going on here? Negative 3 cos 0, okay? And what does this equal? Let's see. Sine 0 is equal to 0. So this becomes 0, all of this is 0, and all of this is 0. So this becomes 3 all over, what is this? Negative 3. All right, negative 1. So the slope of this tangent line here is negative 1. Notice the difference, right? Negative 1 is slope of the tangent line. Negative 3 is the rate of change of that radial distance with respect to theta. Okay, really important distinctions. Let me see. How about I ask you this question? Find all the places find all places, okay, no, here's the question I'll write down. For what values of theta, so at what values of theta, does this cardioid have a horizontal tangent line? So at what values of theta does this cardioid have a horizontal tangent line? And maybe you're one who wants to just, right now preliminarily just eyeball this. Well, clearly there's a horizontal tangent line here. So one would guess that the math should bear out that dy dx equals 0 at theta equals 3 pi over 2. But it looks like there should be a horizontal tangent line here at this value for theta and at this value for theta. And again, we realize that these drawings are hand-drawn, so they're not perfect. But now let's see if the math bears this out. So let's go down over here and take a look at this. We want to know where is that dy dx will equal 0. And if dy dx equals this quotient up here, right, we really care about where the numerator will equal 0. So where is it that r times the cosine of theta plus sine theta times dr d theta, where will that equal 0? Now I'm going to fill everything in here because r here is 3 minus 3 sine theta plus sine theta times dr d theta, which is negative 3 cos theta, right? Equals 0. I think I may have forgotten a cos theta. Oh yeah, see, I forgot to squeeze that into right here. Okay, I'll just squeeze it right here. Okay. Now I'm looking at this and I'm just trying to solve this equation for when theta will equal 0. Well, let's see. I see these two terms here and I'm going to factor out a cosine theta. And when I factor out cosine theta, what I'm left with is 3 minus 3 sine theta plus sine theta. Whoops. Excuse me. 3 minus 3 sine theta minus 3 sine theta, excuse me, equals 0. Is that right? Let me check my algebra. 3 minus 3 sine theta, very good, which then becomes cos theta times 3 minus 6 sine theta equals 0. All right, so we know that this equation will equal 0 when cos theta equals 0, and also when 3 minus 6 sine theta equals 0, which is the same thing as saying when sine theta equals 1/2. Well, between 0 and 360, or 0 and 2 pi, theta equals 1/2 at pi over 6, and then also at 5 pi over 6. And cosine of theta equals 0, theta equals 0, cos of theta equals 0 at pi over 2 and at 3 pi over 2. Now, let's take a look. Theta equals pi over 6 and 5 pi over 6. That seems with reasonable accuracy. Take a look at this. In fact, if I look at this drawing over here, when theta equals pi over 6, so here's theta equals pi over 6, look at that. It looks like it's almost exactly right there on that line. And when theta equals 5 pi over 6, so this is actually not too bad of a drawing. It isn't horribly inaccurate. And here is when theta equals 3 pi over 2. What about this point when theta equals pi over 2? What is going on here? Why is this happening? Let's talk about when theta equals pi over 2. Theta equals pi over 2, if you think about it, when theta equals pi over 2, we are at this point right now. We are at the dimple. Now, that dimple, we've previously called that curvicle feature, or that functional feature, we call it a cusp. Okay, so at theta equals pi over 2, oh no. Okay, when theta equals pi over 2, you'll notice something. At theta equals pi over 2, dy dx is undefined. And why is dy dx undefined? Dy dx is undefined for all the reasons dy dx has always been undefined at a cusp. At that point, dy dx is undefined. Okay. Now, if dy dx is undefined, maybe you're wondering, why did it turn out that when I set the numerator equal to 0, I actually got theta equals pi over 2? Well, it turns out that if you look at dy dx, and if I set the numerator equal to 0, I got those values, theta equals pi over 6, 5 pi over 6, pi over 2, and 3 pi over 2. If I set the denominator equal to 0, and you can do the algebra on your own, if I set the denominator equal to 0, here's what happens. The denominator, when you set it equal to 0, you will find all the points, let's think about this, all the points where, dy dx has a denominator of 0. If the denominator equals 0, you will find all the points that have a point of vertical tangency. Because a point of vertical tangency is a point where the dy dx doesn't exist. If the denominator equals 0, it's a point of vertical tangency. If the numerator and the denominator equals 0, what is required here is further investigation. Okay, so further investigation is required to understand what is going on. And usually that further investigation is looking at the graph. So I know I just kind of said a lot in that sentence, but if you go back to the graph of the cardioid here, if I asked you where dy dx, where this curve has a point of vertical tangency, hopefully you'd see that right around here, like there should be a point somewhere around here at that value of theta where there's a point of vertical tangency. When it comes to the cusp right here, some people like to make the argument that while there isn't a point of vertical tangency necessarily, they say, well, it looks like the lines are like getting closer to vertical as you kind of head into that dimple part. And that's a fair statement to make. But this dimple is called a point of non-differentiability because it's a cusp. And in this case, that point of non-differentiability that is a cusp in the dimple is from dy dx's numerator and denominator being equal to 0. Okay? All right, so in this homework, in the text, you may find cases where the book asks you to find the location of points where there's a point of vertical tangency or of horizontal tangency, and now you know what you need to do. Notice in this case, at this point, given these equations, I was able to solve for theta very comfortably without a calculator. You may find that some of the questions that you do in your textbook, you may have something where sine theta equals something like, I don't know, 7/8, in which case then you'd have to use your calculator because that is not one of your memorized sine values. All right? And have a good long weekend, and I'll see you on Monday. Goodbye.